Thank you to the organizers for putting together such a nice workshop and inviting me to speak here. That's a great honor. I want to present some joint work with Johannes Flake in Bonn and Sebastian Prosur, who also should be capitalized. It was already mentioned earlier, actually, in Mohamed's talk. And this is somebody with a background in pure category theory working with us on this project, which gave it a very interesting sort of new dimension of doing everything in a very general, clean categorical setup. Yeah. So there's a series of 3 papers that I want to summarize some of the results from these papers. Okay, but I want to start with the motivation. So probably many people in this audience care about algebras inside of monoidal categories. So C is a monoidal category. One might want to study algebras in C, but maybe not just any algebras, but rather one might specifically want to look at commutative or maybe commutative Frobenius algebras. So that's good, and this is already come from many areas of research, like extension theory of vertex operator algebras, going back to work of Kirillov-Ostrich or Hornl-Kirillov-Lepowski, or boundary conditions in conformal field theory, especially in work of Ronke-Schweigert, and then étale algebras. Already at this conference, étale algebras, which of course is some kind of commutative algebras. Algebras not just in any monoidal category C, but specifically in the Drinfeld center of the category C, a role in Dimitrij. The question sort of what this talk is about is, like, I mean, okay, first there's a basic question here. If you have functors between monoidal categories, what sort of functors could preserve such algebras? I mean, one clear answer is that monoidal functors, right, especially braided monoidal functors, can preserve commutative. But more generally, there's laxer sort of classes of functors that can preserve them. And I mean, one answer here is that, and if you just want to preserve algebras, it's enough to have lax monoidal functors. But if you also want to preserve Frobenius algebras, or you might want to preserve commutative algebra objects, then one maybe needs, or one class that preserves them are braided Frobenius monoidal functors. And this talk is about building such functors. So sort of the first goal is to find braided Frobenius functors from some Drinfeld center to another Drinfeld center. And here C and D are some monoidal categories. This is not all, this is specific, formulated mostly in the language of general monoidal categories, but you can of course work with tensor categories. Lots of things become a lot easier for tensor categories. Okay, so somehow here asking for strong monoidal functors is too strong of a requirement. Right, I know very few examples of strong monoidal functors between different centers. This seems to sort of be too much to ask. But it turns out that there exists quite a range of sort of lax monoidal functors. Sometimes even Frobenius monoidal functors, but that's more of a special situation. I will also define what that means later, but this is just an overview of what I want to talk about. Now, the question is sort of, why might this kind of thing even exist? And the first time we came across this is actually looking at groups. So if H and G are finite groups, then there's the induction functor. The induction functor is the left adjoint, or in this case, actually left and right adjoint, to the restriction functor of representation categories. And we observed that that induces a functor on.
In characteristic 0?
It doesn't have to be characteristic 0. The functor works in general. And yeah, in general, we can sort of take representations over some field and have this induction functor. And it turns out to be Frobenius monoidal function. This is turned out even a braided Frobenius monoidal functor. We came across this when working with Nate Harmon and on a project a few years ago. In fact, these functors are somewhat implicit in Alexei Davidov's work, because there's this older work of Davidov and then Davidov-Simmons. I want to say 2013 maybe, and this is 2010, where there was a classification of étale algebras inside of connected étale algebras inside of these Drinfeld centers. And there is also sort of a generalization where you take a 3 cocycle. And then it's more natural to look at vect H omega. Here you can restrict the cocycle to H. And then vect G omega to summaries omega. And here, I mean, in follow-up work with Sam Hanna, Ana Camacho, we actually showed that these functors that were sort of on the object level, at least they were a tool in Davidov's work to, if you wanted to classify sort of commutative connected étale algebras in these categories, you can find a subgroup of degrees in which they live. And then, in fact, what the language what one can use here is to say that algebras are all images of some algebras with a one-dimensional degree zero identity degree component induced up from a smaller group. It's the idea. So these functors are useful in classifying certain types of algebra objects in Drinfeld centers. This is the motivation. And what we also used in order not to classify algebras, but just simply to classify objects inside of a Drinfeld center is sort of the topic, I guess, not much at the focus of this conference, but there are these interpolation categories of Helene, where P is a complex number and you interpolate representations of the symmetric groups. And in that sort of setup, we were able to also find a braid. So all of these functors are braided Frobenius monoid functors, all three of them. All appeared in that work with Smake and Harmon. So in fact, you can somehow interpolate classical objects in the Drinfeld center to these interpolation categories, and the assignment itself is a Frobenius monoidal functor that preserves the braiding. So that sort of raised the question of, is this more general? Can we sort of more generally induce a functor on the Drinfeld center? But maybe not from a strong monoidal functor itself, but rather from its adjoint. Adjoint will only be lax monoidal if it's a right adjoint. But then, because this is a conference about spaces of tensor energies, we want to maybe have a little bit more than just an assignment that turns a functor into another functor, but rather we want a functorial assignment. Maybe this can be formulated as the second goal. We would like to upgrade Drinfeld centers to a functor. Now, this functor would start on specific classes of monoidal categories. I'm not being very precise here. You need to make some assumptions on the monoidal categories, which I'll specify in detail later. So I'm gonna just put the word watch here. I'll explain later what that should mean. And then one can take the Drinfeld center, but not just on objects, but also on functors. But if you have here monoidal categories as strong monoidal functors, then it'll be in a contravariant assignment. We build something on the adjoints which go the other direction. So this is somehow from the opposite category of monoidal categories to braided monoidal categories, but not with their normal functors, but rather with Laplace monoidal functors. Now, this is not the only sort of functoriality of the Drinfeld center. There's been earlier work by Kong Liang, which is worth mentioning here, where maybe a bit more in the spirit of this conference, this Morita categories were used. So it was mentioned in several talks that you can build a Morita category here of monoidal categories as bimodules between them as onmorphisms. And in that setup, there's a functor, maybe even a two functor. But so this is sort of a different construction here because we actually take an honest functor and produce an honest functor at the end. It's not an assignment on bimodules. It's a little bit sort of a different construction. And at the moment, I don't know how the two relate. But so, yeah, this is the agenda. Now, the sort of main tool in this are some natural transformations, which we call projection formula morphisms. Now, what are these? So here, we take two monoidal categories and a strong monoidal functor between them. And let's suppose that there is a right adjoint. Now, this right adjoint will become Lax monoidal. This is an old result by Kelly. It is a nice exercise to sort of see what one should try to guess as the Lax monoidal structure, which will then ultimately work out. Lax monoidal structure is something like a monoidal structure of monoidal functor, but it doesn't have to be invertible. So I want to construct a Lax monoidal structure for R. So to have a natural transformation here from R applied separately to tensoring and R. And because we have an adjunction, we can apply the unit of the adjunction. And because this is a right adjoint, it brings us here. And this is already relatively good because G is strong monoidal. I can commute it past the application of these tensors separately. So
when you say strong monoidal, you just mean monoidal, not lax monoidal?
Strong monoidal means monoidal, meaning that the lax structure is invertible.
Okay.
And now that we're here, this is in the correct order of functors, so I can apply co-units. So we can do R of co-unit, tensor co-unit. And now one checks a couple of diagrams that they commute. In fact, they will commute if we make this a lax monoidal structure. Okay, so that's a general fact. And now I can define these projection formula. Oh, I didn't leave myself a lot of space here, but what can I do? So the shape of these morphisms, there'll be a pair of them, a left version and a right version. This is the left version. It will go from A tensor Rx to R, then having here GA tensor X. The natural transformation can be built by applying the unit of the adjunction here, tensored with the identity, brings us to RGA tensor Rx. And now that we are here, I can apply the Lux structure. I just have to apply it specifically to the objects GA and X. And then using here the just constructed Lux structure, that's the monoidal structure, we end up there. Now, of course, in general non-trivial cases, neither of these two morphisms here are isomorphisms. Right? The unit tends to not be an isomorphism. Lux monoidal structure is also typically not an isomorphism. You rarely have a strong monoidal functor with a strong monoidal right adjoint unless you have an equivalence. It's a rare situation. So, but somehow in most situations one might care about this projection formula morphism in fact is an isomorphism. And then there is an analogous version here on where we just do everything the other way around. So this is called RProj, and I will need both of them. RProj goes like this. Now, maybe it's sort of an interpretation of why are these morphisms from that place to that place. It's sort of, it makes a lot of sense if you think about A here as acting on Rx on the left with the regular action. So this is something like, because here we are inside of the monoidal category C, and A was an object of C. So this is like A acting on X with the regular tensor product action. And this you can view as functor R applied to A acting on X, not with the regular action, but rather with some sort of pullback of the regular action of E along that monoidal functor G. And when you then look at this, it looks like this makes the functor R a functor of left module categories. This type of morphism one needs there, and it needs to be invertible. And it needs to satisfy a bunch of coherences, what one has to prove. Prove those in the paper. So similarly here, this is Rx, and you have a right action of A on it. This is Rx with the right action of A on it, with again with this sort of back action. So these are the projection formula morphisms. I need to make some comments to put these in the context a little bit. So they actually go by a sort of different name in a certain sort of branch of the literature, which concerns itself with Hopf monads. So in the literature of Hopf monads, typically you will have a left adjoint for G. And then there is also projection formula morphisms. They just go the other direction, but between the same sort of objects for the left adjoint instead of right adjoint. And these are called Hopf operators in this theory of Hopf monads, because in the theory of Hopf monads, they tend to just name it after Hopf because they were studying Hopf monads, and these operators were quite crucial in order to have a Hopf monad. So there is that name, but we only found out about that if we had already sort of committed ourselves to that name, which comes up a lot in the algebraic geometry literature. And there was a paper by Pausk, Hu, and May from topology that studied these also in a context of closed symmetric monoidal categories. This is how we first came about it, sort of what inspired the naming. But yeah, these are quite well used natural transformations. And maybe at this point I can give a sort of quick example. This example comes from Hopf algebras. So we have now a morphism of Hopf algebras. These are just morphisms of Hopf algebras. They don't have to be finite dimensional Hopf algebras. It doesn't have to be objective. But with that, we can define the restriction functor from H mod. This could be all modules, doesn't just have to be finite dimensional modules in order, and that has a sort of right adjoint, which is co-induction. The co-induction is the right adjoint. Of course, if I wanted the right adjoint to even restrict to finite dimensional module categories, I need to make more assumptions. This doesn't always work that well, but in general, you can write down a side adjoint conjunction. And it's specifically in that setup, one can write down what this projection formula morphism is for two modules. And coint is given by Hom from the large Hopf algebra over the small Hopf algebra into the module V, which is just a module over the small Hopf algebra. And the projection formula morphism should now go to Hom K from H, and here we'll have, so W would now be restricted to K and then tensored with V. So, and here we can write down what this would be very concretely. We can take elements W tensor F and send them to a function. This function takes an input H, and now we should take H1, let it act on W, and apply the function to the other outputs. So H1, H2 is the co-product of H in Sweetler's notation. And one can use the antipode of the Hopf algebra here in order to construct an inverse for such map. So in this case, it turns out to be an isomorphism. Okay, and then there is a proposition here. And the general form of the proposition I want to state to this audience is that, I mean, a special case sort of is if your monoidal categories have duals. So if they're rigid monoidal categories, C and D, then these are always isomorphism. That's the short form. But it is more general than that. You can also say that if and the image of G inside of D have left and right internal Homs, and we require that G preserves them, then L-Poch and R-Poch are isomorphisms. In this situation, we refer to as saying that the projection formulas hold. But you can see here, I mean, a special case of this would be if you have duals, and then the strong monoidal functor G would automatically preserve them, so that condition is satisfied, and then left and right Poch are isomorphisms. But we can already see there's many non-rigid situations which this holds, because here in this example, I can take categories of all possible modules over these Hopf algebras and HB info, no? But if they're Hopf algebras, then still these are isomorphisms, so rigidity is not necessary as a condition. Are there any questions at this point? So I already explained here on this board was that this observation that if R-Poch and L-Poch are isos, then the right adjoint is a functor of phi modules. So this is, one has to check a bunch of coherence diagrams, but this will be true. So as soon as these are isomorphisms, they have sort of the correct shape to give the diagram of of a functor of bimodules. So computing the left and right C action, and here this means we consider D as the C bimodule using the functor G. Okay, now if that's true, then we can make use of, so I said earlier that the Drinfeld center is not naturally functorial for monoidal categories, but the Drinfeld center can also be defined for bimodule categories. So at this point, I mean, I never defined the Drinfeld center because I imagine that probably most people are very familiar with it, but I can define the center of a bimodule category. So for MAC bimodule, we also have the Drinfeld center Zm, and this has objects. If we note them by M, C, C is also associated with M, and C is a natural isomorphism, which has components. M acted on the right by X acting on the left by M. And this has to satisfy some coherence with the tensor product. And if we now assume strictness for the moment to make write down an easier formula, the coherence is something like, if I evaluate this on a tensor product, it's the same as composing the individual half braiding. So there's such a structure we call the half braiding here in this context. So we can still apply the half braiding to Y, and apply it to X, and then apply it to Y, acting here on the Y axis. And morphisms are simply morphisms of the underlying category M, which satisfy a commutative diagram with respect to these half braidings. So this definition. Yeah.
In that proposition, there's an if then statement. Is that actually an if and only if statement?
Well, we also show that if you have a structure of bimodule categories, then it has to actually be the one coming from. Wait, is that correct? You know, I have to look into the paper. In some senses, it's quite a canonical bimodule structure. And of course, the construction wouldn't work as if these aren't isos because you don't have a candidate for the coherences. But I don't know if maybe out of nowhere you could have a different coherence, but I think we ruled that out in the paper. Okay, so what do we want to say? So there's some references here for the specific category that we're interested in, M equal DG. This is actually quite an old definition already around the time when the Drinfeld center was introduced by several authors. Majid already proposed this definition. But sort of more generally for bimodule categories, the earliest reference I could find was a paper by Gilaki, Naidu, Niksic, 2009. I guess the idea, yeah, that such a generalization appeared. And but what is nice about this construction is that it's actually two functorial. This is a proposition that one can find in a paper by Shimizu, where it says that the Drinfeld center of bimodule categories is two functorial. Well, here's actually a disclaimer, so this doesn't always give us a monoidal, right, in general. In this specific case, where M is equal to D and the action comes from the monoidal functor G, then you get a monoidal category. But in general, we don't. So this assignment is just a two functor from C bimodules to categories, category of category. And that we can now use. And now apply this to the, I guess, sort of situation of this adjunction. So one can make this sort of entire situation a little bit more formal. One can say that this type of situation where you have a strong monoidal functor with a joint is the datum of an adjunction internal to a two category or monoidal categories where the functors are just lax monoidal. Because if the functors are lax monoidal, R is a well-defined functor and not but G is also lax monoidal, but because it's the left adjoint, it's also O-lax monoidal, just sort of by that theorem, then becomes strong monoidal. So this is actually, this sort of setup is equivalent to saying we have an internal adjunction to the bi-category, or two category, in fact, of monoidal categories with lax monoidal functors and monoidal transformations. And in fact, for any sort of bi-category like this, if we have some sort of two functor, it will involve internal adjunctions. And for that reason, we can now say that Z blank will preserve adjunctions. And also monoidal structures, lax monoidal structures. So if we now apply, if we start again with this input datum of the monoidal adjunction, but now at every point, I want to think about it. I want to think about the functors as lax monoidal, but also as bimodule functors. So I mentioned specifically that here for D, this is R is a functor of bimodule categories. Of course, since D is also a functor of bimodule categories in sort of an easier way. So for both of these, we can apply the center construction. Now we have a junction here. And we still have that Z of R as a lax monoidal functor. And this means we kind of arrive at a result, which I want to call theorem A in the hope of being able to talk about the other results briefly. And in the spirit of this conference, I want to raise it as a functor. So I want to say that the assignment of sending C to its center. So this assignment starts with monoidal categories with strong monoidal functors, which have right adjoints that satisfy the projection formula morphism, projection formula identity. So some sort of subcategory of the category of monoidal categories, functors between them. So now this is contravariant because we build something on the adjoint. And then we go to braided monoidal categories where the functors are just lax but braided. So this is some extra thing one needs to show. So I guess I haven't quite finished the story here, but what this does on functors, if I have a monoidal adjunction, one chooses an adjoint. So, and now we have this functor ZR going from the center of BG to the center of C. But we can, of course, I mean here, and include the actual Drinfeld center of D. So here, these are objects in D that have half braidings for every object in the image of the functor G. But that means if I had an object that had a half braiding for every object of D, then in particular I can restrict the half braiding just to functors in the image of G. So one can in fact include as a monoidal subcategory with a strong monoidal functor the Drinfeld center into this relative Drinfeld, this sort of dual category.
Some people use a subscript like sub C in the, that's mysterious and
Yeah, maybe it's better to put a subscript.
yeah.
This
Sub C in the middle in
But then this is in fact the actual Drinfeld center, as one knows it,
well, is not.
and that one is not. Yeah. But this one again is the normal Drinfeld center. So here's this functor, and maybe then we call this ZC, which actually helps my notation quite a lot, because I want to call this composition Z of R. So this helps my notation. Yeah. So this, and then, I mean, up to choice of adjoints, I guess. But if you choose adjoints coherently, if you choose an adjoint for the composition, so if you have a diagram of two monoidal functors, G1 and G2, and I use adjoints, right adjoints. And then to get an adjoint for the composition, I allow myself to use the composition of adjoints. Then for this situation, adjoints will have to compose, but then this functor is going to be the same as composing the induced functors on the center. And so this is a construction. So there's no statement here, function is functorial. Such that in such a situation is a composition law here, but now what is actually instructive, I think, is to write down how this functor concretely looks like in the half braiding description of the Drinfeld center. Because that shows like how the projection from the morphisms are relevant in the construction. I take an object x and cx in Z of C, and this is mapped to with this functor to the following object. So you apply the functor to the object component, and then we define half braiding. The half braiding evaluated on some object A. Find this composition. So where do we need to start here? We need to start with Rx tensor A. But here we can use the projection formula morphism, which I unfortunately just erased. It's the right version of it, which will bring us to R x tensor GA. And here I can apply the functor R to the half braiding of x evaluated on the object G. That brings me to R GA tensor x. And then in the final step, we apply the other projection formula morphism, but it's inverse. Which brings us back to A tensor Rx. Now this is a composition of isomorphisms, so we can define, we can take this composition of all of these isomorphisms, that'll be the half braiding of Rx. So directly there is the projection formula morphisms appearing just in the definition of the functor already. Now this is part of the statement here, so that's a Lax monoidal functor, and in fact it inherits directly the Lax monoidal structure of R. So that means implies a claim that the Lax monoidal structure of R is in particular morphism in the Drinfeld center, but that checks out to be the case. So the Lax monoidal structure actually doesn't change, it's the original one that R had.
The half braiding invertible.
Yes. The half braiding has to be invertible, but we assume here as a crucial assumption that these projection formula morphisms are invertible. And then, of course, also here the middle thing is invertible. Okay, so maybe it would be nice to mention briefly some example. So maybe slightly more geometric examples. Taking a fine algebraic group, let's say over C. And then we define purely algebraically rep G as comodules over the coordinate ring. These are all comodules. And then I can suppose that I have a. So, and then one can ask, what is the Drinfeld center? It can here be identified with the category of OG modules internal to this category rep G. This can be interpreted as what should be Cartesian sheaves on the quotient of G with vectors in the joint angle. So this point of view in the Drinfeld center was also studied in a higher category or infinity categorical setup in the paper by Ben Sui, Francis, and so this, although here we don't do infinity categories, but now if I have a morphism of such affine algebraic groups, schemes, say group schemes. So then we have a restriction functor, which algebraically is just restriction or co-restriction of comodules. And now the theorem. So here we have in a joint, a right adjoint, in fact, induction here, comodule induction, or cone, one should call it, if the right adjoint in the other direction. So one gets a lax monoidal functor that is compatible with bindings. From the Drinfeld center of the smaller group to that of the bigger group. Because I mean, this can be done, of course, generally for Hopf algebras. This is just case.
So these are equivariant coherent sheaves.
Yeah. Yes, you can see it that way. But I mean, in order to prove things, I just use this model. Okay, so this is sort of the first part of the talk. So are there any questions?
You mentioned in between that you are following rotation or namings from algebraic geometry.
Just the one terminology, projection formula morphism.
But that's all. So you're not
Yeah.
required by applications in algebraic geometry.
Not originally, no. This was just inspired to find some functors between the Drinfeld centers. But it then turned out that this projection formula morphism is a crucial.
I have a question. Is there maybe some universal property that